Hello, this is question 3 from the 2010 MAT. In this question, you may assume that derivative of sine x is cos x. Okay, fair enough, we'll probably do that anyway. First part of the question, in the diagram above, OA and OC are length 1. Okay, let's mark those on, OA, OC. Subtended angle X at O, they've already got that in the picture. The angle BAO is a right angle. Circular arc from A to C centered on O is also drawn. Right, by consideration of various areas in the above diagram, show that for x is greater than 0, less than pi by 2, that we've got these inequalities. So by consideration of the various areas, we've got 3 things here in our inequalities, and we've got 3 different areas. So it seems to be asking us to work out the different areas then. So let's do then the area of triangle OAB. Let's start with a big one. And that is going to be, so half base times height. So we got half of BA, well, half of AB. So AB, we're going to have to do some trig then. So tan X is opposite over adjacent, which is AB, right? So that's a half tan X. That's a good start. Okay, admittedly, it's not one of the 3 terms we got in our inequality, but we can always get a sine out of a tan, so that's not necessarily too bad. Now let's go for sector OAC. That's the next biggest one. So that is a sector of a unit circle. So the area of the whole unit circle is going to be pi, because obviously r is 1, and then we need to multiply by x divided by 2 pi. So that is x over 2. Okay, so that's giving us something to work on with the x there. Then we've got that, the little triangle. So triangle OAC is what we got there. It's isosceles. We got 2 sides of length 1, and we got the angle between them. So a half AB sine x. So that's just going to be a half of sine x. Okay. So we've got then on this that, well, these are in decreasing size. So, well, let's do the nice ones here. We know that the half sine x, the smallest one, that has to be less than x over 2. Well, let's write them all out, which has to be less than a half of tan x. Okay, so we can get rid of all these halves. Get rid of all of those. So we've got one of them then. We've got our sine x is less than x. That's cropped up here. Now we can do the, oh right, and yeah, it's going to drop out because on the last 2 then, we just multiply through by cos x. And we know that cos x is positive because we're just going from 0 to pi by 2. So we can multiply that by cos x, and then we get x cos x is less than sine x. And lo and behold, it's all dropped into place. Right, so that kind of fell into place, groping in the dark as we went along. But at least they told us what to do. Consideration of various areas. So just follow the instruction and see where you end up. So that's not bad. Right, part 2 then. Let's change over to blue. Sketch on the axes provided, which I'll put down in the bottom right here, the graph of y equals sine x over x, 0 to 4 pi for x. Justify your value that y takes as x becomes small. Yeah, indeed, because we've got 0 over 0. You do not need to determine the coordinates of the turning points. Okay. Well, we know aside from when x is 0, which we can come back to, we got, I mean, this is a damped oscillation. You see a lot of these in physics anyway. So we're going to get a 0 value for y for every multiple of pi for x. So we know we're going through these points here. And the amplitude is going to be decreasing because we got a regular sine wave, but x is just getting bigger and bigger. So it's going to be damping down the amplitude more and more as we go on. So we know that we're going to have something that's looking like this once we've got past pi. So that's fine. It's what happens as x tends to 0. And if we got that 0 over 0, then what do we end up with? Do we end up with 0? Do we end up with infinity? Do we get 1? Do we get something else? So we're comparing sine x with x, which have featured in the first part of the question. You know, as is usual with these things, if they're throwing in something that's a bit weird, you've probably already done something to help. So we've said here then that the area, this is like comparing. So let's start off. So from diagram, then we can say that sine x is two times area of, which one was sine x? Triangle OAC. Triangle OAC. And x is 2 times the area of the sector, wasn't it? Yes, the sector OAC. Right, so we know we're comparing these areas on the picture then. So the difference between those two areas is, well, it's this little bit here. I mean, you could just color that bit in and say is region shaded. Okay, so that's telling us the difference. Then we can step off and say, right, as x tends to 0, the shaded region tends to 0. Now that's what we're going to get as we're shrinking x down. We're making that angle smaller and smaller and smaller. That area is just going to get smaller and smaller. The difference between these two regions that we're looking at. So the area of the shaded region tends to 0, which means we're going to get the area of OAC is tending towards the area of the sector OAC. Therefore, sine x tends to x. I mean, that's well, actually, I suppose we could have just said that straight. I mean, the picture helps, but I mean, maybe we could have said this. You could have done some kind of derivation of a small angle approximation, something like that. Maybe something like that. But this picture is here. I mean, it's more or less what you'd be doing anyway. So if the picture's there, let's just work off it. Sine x is turning to x. Therefore, y equals 1 when x equals 0. So that means we're going through here and we can connect up the last bit of our damped oscillation. So that's good. We don't need the turning point, so we've done that bit. Part 3, drawn below, well, over here, we'll put it on the right hand side, is a graph of y equals sine x. Yep, okay, they give us the easy one. Sketch on the same axes the line y equals cx, so a straight line, gradient c, so positive gradient, is such that the equation sine x equals cx, if I can get my words out, has exactly 5 solutions. Right, so we want a straight line which has to go through the origin, so that's one solution, and we need exactly 5 solutions, and it's got to be a positive gradient. So we're going to cut this one, well, we need 2 on either side, so it's going to have to just be touching here, go through there, because that gives us 1, 2, 3 if that's tangent, and then tangent on that side, which gives us 4, 5. Right, okay, they didn't want much there for part 3. Draw the line y equals c on the on this picture. So when they're saying the axis on the opposite page, is this picture that we've drawn. So we've done a dampening of sine x in this picture in order to create this one. And now we need to move this graph across onto that. So let's change to green. So what do we know about this? It's going through, so this is the line y equals c, so it's a horizontal line, and this horizontal line, so if you've got y equals c that we've drawn on there, so we're saying that c is equal to sine x over x. So yeah, so they're going to intersect in the same place, because we've got that c is sine x over x, so cx equals sine x. We're just doing a transformation from one to the other, so it must be tangent on the second peak. So it must be tangent to here. It's going to be a horizontal line, which I'm not going to be able to draw very well on this screen. But yeah, horizontal line tangent to the second peak, because that's exactly what we've got in this first graph. Okay, right, I'm liking this so far. If capital X is the largest of the 5 solutions, to the equation sine x equals cx. So we're saying that this coordinate here, this x coordinate, is capital X. Explain why tan x equals x. Right. How do we know what to do with this then? So they've just asked us to draw this twice though. And so what do we know? So we've got to get a tan x. X is the largest of the 5 solutions. So we're either looking at that point there or we're looking at this point here. But both of them are essentially the same, but they're both tangents. So it's got to be something to do with that. We know that we've got a tangent line on these. So let's just go off we've got this sine x equals cx. So we can say when little x is equal to big X, we can then say that the gradient of each line of sine x is equal to the gradient of cx. All right, so this does help. Actually, because we haven't used this bit right at the start where they were telling us to assume the derivative of sine x is cos x. So at least it fits in with that. So that means that we've got that. So the gradient, so cos x, so cos capital X, i.e., is going to be equal to c. Okay, so we've got cos of capital X is equal to c, plus, of course, we just got this sine of capital X equals c capital X. So let's divide them. And that's great. That's going to give us our tan x, and it's going to get rid of the c's. Yeah, excellent. So we can divide each side by these. So we divide that by the cos x, and we'll divide that by the c, and we get tan x is equal to x. Right, okay, that fell out all right as well. Right, that was, yeah, it didn't end up being that bad a question, but it was certainly one of those ones, with maybe the exception of the graph sketch in the middle, where the end point wasn't obvious. It was just kind of following the trail maybe on each part of the question and hoping it ended up in the right place, which they all did relatively straightforwardly. I mean, it's not a trivial question, but I don't know, I always felt as I was slightly uncertain all the way going through it, but every bit of it just dropped out quite nicely. But I suppose they are giving little hints all the way through. You know, consider the areas, and then what have we got? Oh yeah, about giving this hint of looking at a derivative and things like this. So yeah, it was certainly being guided in the right direction. But yeah, that one, I think it was a bit easier than question 2. But I don't know, 2010 so far feels a little bit more difficult than the 2009 paper. But we'll see how question 4 gets on in the next video.